All right. Hello. Hello, everyone. Okay. Just a second. Get everything ready. All right. Okay, can I ask how many, so today we do physics. How many problems for physics have you managed to do? You can put an S if you haven't started. 7 NS. Okay. Got a few. Okay. Starting today, yeah, good. Good idea. Okay. Let me just download the latest version for physics. That's physics 03. Okay. Mhm. Okay. I just wanted to explain what the first section is about, because it's some people can find this a little bit vague. Right, so I'm going to share my screen. So where's the... Okay, here it is. I started the math paper first. Okay, no, thanks. We don't have any physics. Okay. Right. Let's share my screen, and here we are. So hopefully, you should be seeing my screen, and it should be recording. Yes, so it is a recording. I am sharing my screen, and let's go. So the first section, well, Newton's first law. Newton's first law deals with frames of reference, and I explained that last week. So there are the Newton's first law states that there exist inertial frames of reference, and that's a very important part of Newton's first law, which is omitted in school textbooks. The inertial frame of reference, for example, a train moving at constant speed, this is an inertial frame of reference, but an accelerating train is a non-inertial frame of reference. And the first problem gives examples of 3 inertial frames of reference. Well, that's fairly simple. I give example of 3 non-inertial frames of reference and describe an experiment which you can conduct to show that it is not satisfied. Well, as I was explaining, if you are in a train, for example, and you put a tennis ball on the floor, you are in the frame of reference of the train. And if the train starts to slow down, This is a non-inertial frame of reference. So you have a ball on the floor of a train, and suddenly it starts accelerating. So that is how we know that, well, Newton's first law is not satisfied in this reference frame. Because in inertial frames of reference, if you have a ball on a table and there are no forces, it will remain stationary. But in an accelerating frame of reference, that's not the case. Okay. Newton's second law. So what we're trying to show you here is like how to define mass and force. Okay. And I'd like to ask you a question. How do astronauts find their mass? Because I mean, if you're an astronaut, it's important to keep healthy. So let's say you're on a space station, you live there for 3, 4, 5, 6 months. I don't know what the record is, but I think it's quite long. How do you measure your mass? You're weightless, right? So what do you do? Does anyone know? Chat. How do you? Ooh, good, Haroon. Yes, in fact, they do. They do use a spring. Do you know how? Let's call it problem 0. How do astronauts find the impulse? Well, potentially. Can you clarify what you mean? The spring constant stays constant, true, but so what? Then push some constant force and then measure acceleration. Compress a spring and make it push you with some constant force. You can measure the force. Okay. Yes, I mean that's a good idea. So idea number 1, you have a known force, and A equals ma. So m is the force divided by acceleration. So apply a known force to the astronaut and measure the acceleration. And by measuring the force and acceleration, you can find the mass. Good. So how would it work? Well, you would probably take a force, like a force meter. So take the astronaut. So this is the astronaut. You tie the astronaut. You hook the astronaut to a force meter, the type of force meter that you have in school. This is a force meter. Apply a force, let's say F equals 1 Newton, and measure the acceleration. I mean, they don't actually tie force meters to astronauts, but yeah, it's a very good idea. Acceleration, yes, light gates or slow motion cameras, absolutely. Yes, so you can find acceleration that way. Another way, you can tie 2 astronauts together. Tie 2 astronauts together with a spring. It's a compressed spring. So this astronaut mass m1, mass of astronaut mass m2. is compressed spring. The spring is released, so that's the first method. The second, the spring is released. Spring released. And one astronaut accelerates right, one astronaut accelerates left. The acceleration of the first astronaut is A1, the acceleration of the astronaut A2, and you have M1 A1 is equal to M2 A2. In other words, to find the astronaut M1, you take the astronaut of known mass M2, A2 divided by A1. So you measure the accelerations of both astronauts. If you know the mass of astronaut 2, let's say we have a standard perfectly spherical astronaut of mass 1 kilogram. Yeah, and then we can, this becomes 1. So M2, mass of M1, mass of the first astronaut is simply A2 divided by A1. So if the second astronaut is 1 kilogram, well, I mean, actually, it's like a mass of 1 kilogram, of course, not an astronaut, just in case you're wondering. So yeah, tie a known mass and measure the acceleration. So, and it has nothing to do with gravitational force. Okay, so it's not a gravitational mass, it's inertial mass. This is called inertial mass. Inertial mass. Inertial mass. But funnily enough, inertial mass and gravitational mass, how they say, have the same values, which is quite peculiar. We don't know why. Inertial and gravitational mass have the same value. So, well, yes, they're defined differently, because if you have the gravitational force is equal to G M1 M2 divided by D squared. This is the mass that creates a field around itself. That's mass, gravitational mass. And in F equals ma, you have inertial mass. And if mg is the only force acting on you, then mg equals ma. And now here on the left we have gravitational mass and inertial mass, and they cancel out because they are the same. That's why in the field of gravity your acceleration is g. So this is quite peculiar. Well, we haven't discovered any deviation so far, as far as I know. I'm not the leading edge scientist in this topic, but as far as I know, there are no deviations whatsoever. So they are exactly the same. Anyways, going back here, we can define mass as the ratio where we take one of the m's, like a prototype object whose mass is 1 kilogram. Now this choice is arbitrary, as you can understand. 1 kilogram is not something out of nature, it's something we invented. 1 kilogram is what is the difference between gravity and inertial mass in terms of concepts? So Vin, look, gravitational mass is what kind of gravitational field is how it interacts at a distance with other objects with mass. You know, we know that two objects attract due to m1 and m2. Any two objects in the universe will attract with a force F. Now, and this is the gravitational mass, which determines gravitational mass determines means gravitational attraction. Now, inertial mass determines the inertial mass determines means how difficult it is to get something to move. If that makes sense. If you apply a force F, and how does this react? So acceleration is force over mass. So mass determines how quickly it accelerates, and here mass determines how strong the gravitational force is. They seem to be completely different things, but they are exactly equal to each other. Which, well, at least no experiment has been able to find the difference between the two. So yeah. Anyway, we have a prototype object of 1 kilogram, and we can define the mass by comparing it, by comparing the accelerations of two interacting objects. Okay, so if you have a mass m1 and you have a mass of 1 kilogram, and they interact, they do something to each other, and they start accelerating. So one accelerates one way, one accelerates the other way. So the mass is defined as the ratio of accelerations, A1, multiplied by 1 kilogram, which is, well, 1 kilogram. So yeah. And then if we look at this, in this, we just define the force as mass times the acceleration. So we've defined the mass. The mass is the ratio of accelerations, and mass times acceleration we define as a force. So this is, you can use this. We use this as a definition of a force. So the question is, what is a force? Well, it's the product of the mass. The mass is defined here, times the acceleration. The acceleration is very well defined, so it's very easy to understand what acceleration is. Mass, on the other hand, is much more difficult. Okay, and oh, sorry. I have my favorite XKCD comics is this one. There are 4 fundamental forces between particles. Gravity, which obeys this inverse square law. This is the formula for gravity. Okay. The second is the electromagnetism, which obeys this inverse square law. So the electrostatic force yeah, we understand this very well. And also there's Maxwell's equations. And then the strong nuclear force, which, well, it holds protons and neutrons together, and it's strong. And then there's the weak force, something about radioactive decay, something. And those are the 4 fundamental forces. So basically, it's a person who has very little understanding on what the forces are about. But then my favorite phrase is the next one. There's one of the forces which we know nothing about. There is one of the 4 which we know very little about. And then which we don't I don't remember the exact phrase, which we don't know how it works, don't know anything about. It's gravity. Okay, so we haven't figured out gravity, pretty much. Like the scientists, physicists, well, physicists have not figured out how gravity works yet, as of yet. And we have the standard model, which explains, the standard model combines these 3 forces. Standard model. But then there is Newton's general theory of relativity, which describes gravity pretty well, but there's no law that explains everything. So we either explain everything except gravity, or we just explain gravity without explaining the rest. Okay, so Newton's Einstein's theory of general relativity does not explain the other 3 forces, and the standard model doesn't explain gravity. So we know very little about gravity, as a matter of fact. Anyways, going back here. Newton's 3rd law: when 2 objects interact, they exert equal but opposite forces on each other. And we can see that N2 simply is the definition of a force. So Newton's 2nd law is the definition of the force, and N3 is an experimental fact, okay, which we have, which we know to be true. Okay, so hopefully I've confused you. Hopefully I've genuinely confused you. Gravitons, well, they haven't been discovered yet, and perhaps never will. We don't know. That's the thing. Okay, so today I'm going to go through 5 pretty difficult problems. So bear with me. But what you will understand, that most of these problems concern Newton's 2nd law, and they follow the same algorithm. Okay, and the algorithm goes something in the lines of, so solving problems on Newton's laws. Step 1, draw body diagram, for each body. 2, write Newton's 2nd law for each body. 3, make a set of simultaneous equations. Oh, step 3 is step 3 for every single physics problem. Yeah, because as I have mentioned, if you cannot get a set of simultaneous equations, the problem is unsolvable. Okay, so this step 3 is true for any problem, true for any problem, full stop. Because yeah, that's pretty much, if you break down any problem, it comes down to simultaneous equations. So let's look at problem 1 and follow this algorithm. And this is a solid algorithm. You just need to understand how it works. Draw free body diagram for each body. Okay, so let's start with the easy one, M3. What are the forces acting on M3? Well, the forces acting on M3 are the tension. Now these are 2 ropes with 2 separate tensions. So I'm going to call this T2. And there's gravitational force M3G. Now I need to decide whether the system will move up or down. Okay, so M1 is frictionless and M2 has a friction 0.3. Now M3, well, what's your guess? Will M3 move down or up? What do you think? Yeah, it looks like it's going to move down. Now, you don't need to worry if you get it wrong. Okay, so I'm just going to write down, it will accelerate downwards. It will accelerate downwards. And now I write Newton's second law. It's very important to do it very accurately. Newton's second law is written in the following way: mass times acceleration equals resultant force. Now, mass times acceleration, so M3 times A, because we know the mass, M3 times A, is equal to the resultant force. The resultant is the forces in the same direction as acceleration minus the forces in the opposite direction. So M3G minus T2. And this is Newton's second law for the third mass. Okay, now we go on to the second one. So we take the second one, M2, the forces, so there's tension T1, there's tension T2, there is the weight, then there's the normal reaction, and there is friction on M2. Okay, friction on M2, and this friction is going, well, since we've decided that it slides up the slope, then the friction is in this direction. So friction this way. So label the forces. So that's T2, that's T1. This is N, well, N2. This is M2G. And then there is mu N2, because there's friction, okay? And friction is equal to mu times N2. Good. So we split M2G into components. Now, if this angle is 30 degrees, this angle is 30 degrees as well. Not. This angle is 30 degrees, sorry. Moment of madness. Yes, this angle is 30 degrees. You can verify that. If you imagine the angle getting smaller, you can see that this angle also gets smaller. So when that angle is 0, this angle is 0. But there are different ways you can work it out. This is done geometrically. So this is 30, this is 30. I'm sure you can work it out. I don't want to pause here too much. So this component is going to be M2G cos 30. And this one is M2G sine 30. Okay. Now I write Newton's second law. Now it looks super complicated. Actually, it's not. It's not. We need the we need to choose a direction. Let's choose this direction. This is the x-axis. Now, in these problems, you always put the x-axis either down the slope or up the slope. The y-axis is perpendicular, but we don't need the y-axis here. So I'm just gonna drop it because the mass is not moving along the y-axis. It's not moving perpendicular to the slope. The mass is not moving in that direction, which is the y direction. So it's only moving in the x direction. So mass acceleration is equal to resultant force. So m2 times acceleration up the slope. It's the same acceleration as in the previous one. So we use the same letter A. Mass acceleration is equal to forces up the slope, so T2, minus forces down the slope, so minus M2G sine theta, sine 30, minus T1, minus mu N2. Okay. Oh, well, as a matter of fact, we do need the vertical forces. Okay, vertical forces. We'll write them separately. Vertical. We have N2. N2 is equal to M2G cos 30. Because this force is balanced with this force. Because that's the only force up. This is the only force down. All right. Are you still with me? How well do you understand what we have done so far on a scale of 0 to 10, please? Okay. Do ask me if you want me to clarify something, or if you feel that you can rewatch that and get a better understanding. Why friction is mu N2? Well, friction, because it's sliding, and that's if sliding, friction is equal to mu N. That's it. If you're sliding across a surface, the coefficient of friction is mu, and the friction force is mu N. That's which component is sine or cos? Well, if you have a force and an angle, the component next to it with the adjacent, well, we can call it the adjacent component, is F cos theta, and the other component, this is F sine theta. I urge you to memorize this because this is this is so important that this was the first assignment. Okay, if you don't if you're not solid with this, please go back to the first assignment and really study this correctly. Sine is slide, cos is crush. A nice one. I like this, but yeah, whichever way works for you. Vertical. So we can, because n is equal to m2g cos 30, we can plug that in here. We can plug that in here. And we have a rather complicated m2a is equal to t2 minus m2g sine 30 minus t1 minus mu m2g cos 30. Now, this looks incredibly complicated, but I assure you it isn't. Well, it's somewhat complicated, but not the end of the world. Oh. Okay. And that's the second equation. That's the second simultaneous equation. And that's Newton's second law for the second mass. Now we write down Newton's second law for the third mass. Third mass. And it's the same principle, third mass. Oh, sorry, first mass. First mass. This is the second mass. This is the third mass. This is second mass. This is the first mass. But the first mass is going to be slightly easier. So this is M1. So this is M1G. There is tension, T1. There's normal reaction. And that's it. There are no other forces. So this is N1. This is T1. And this is M1G. M1G, we split into components. M1G cos 30. M1G sine 30. And it's accelerating up the slope. It's accelerating up the slope. So M mass acceleration is equal to resultant force. So M1A is equal to T1 minus M1G sine 30. And that's the third equation. All right. And now we just plug everything in. We take the first equation. So M3 is 4. So 4A is equal to 4G. G is 10. So 40. 40 minus T2. Then we have M2 is 1. So A is equal to T2 minus M2, which is 1. 1 times 10 times sine 30. That's 5. I'm using the second equation. So this one is here. This one is here. Minus 5 minus T1. Mu n is an experimental fact. Yeah, it's proved by experiment. It's not it's a purely empirical law. T1 minus mu, which is 0.3, multiplied by M2, which is 1, multiplied by 10, multiplied by cos 30. Cos 30 is square root of 3/2. And finally, the third one, the third equation is this. M1, which is 3 kilograms, 3A, equals T1, which is, well, T1, this is what we are looking for, minus M1, which is 330, times sine 30, which, well, times a half, times 0.5. And look at this. Three equations, three unknowns. Three equations, three unknowns. So all you need is just solve it, just like any simultaneous equations. Okay, so you would add the yeah, I mean, there are different ways how you can do it. Okay, you can do it on a calculator. It's just simultaneous equations. So you would have, okay, so what can you do here? So 4a equals 40 minus t2. Now you can add the second and third one. So 4a is equal to t2 minus 5. T2 minus 5 minus 15, so minus 20, 3 times minus 3 square root of 3 over 2, and subtract that, and you get 2t2 is equal to 2t2 minus 60 minus 3 square root of 3 over 2 equals 0. T2 is equal to 30 plus 3 square root of 3 over 4. So we found T2. Then you, in a similar way, you find T1 and you find A. Okay. Yes, adding them all. Oh yes, absolutely. Adding them all cancels the tensions. So yes, you can do that. Pretty much. Okay, not the easiest question in the world, but let's go back to the algorithm. Draw a free body diagram for each body. Write Newton's second law, make a set of simultaneous equations. That's exactly what we did. We draw a free body diagram, we write down Newton's second law. We draw a free body diagram, we write Newton's second law. We draw a free body diagram, we write Newton's second law. And always remember, Newton's second law is not written equal F equals ma, it's ma equals resultant force. And by resultant force, we actually mean forces that help you move. So forces forward minus forces backwards. And if you remember this strategy, you will have no problem solving even the hardest ones, even the hardest problems. Okay, problem 2 is somewhat simpler. Two blocks are placed on a smooth table. The coefficient of friction between the two blocks is 0.4. Find the acceleration of the bottom block if F equals 2n. Okay, if F equals 2n and if F equals 40n. Let's have a look. So let's label block 1 and block 2. So block 1, the force is acting. We draw the block. So we follow the same algorithm. So we have the mg, we have the normal reaction, and we have a horizontal force, F. Is there any other force on the first block? Friction. Yes, there is friction, and friction left or right? Is friction left or right? Friction to the left. Well done. So I'm just gonna slightly modify this. So mg is from the center, of course. Now n is applied at the bottom, yeah, because it's a normal reaction, so it's applied at the bottom. And there's friction at, we say that friction is applied at the same point, which is equal to mu n. Mu n. Okay. So from here we can see that n is equal to mg. That's easy. Sorry, let's call it n1 because we'll have n2 as well. N1. So your block, you're the top block. What do you feel? So you feel there's friction. Somebody's pushing you from the back. Yes. Then your feet are on the ground. So there's friction. You can feel that. There's gravity pulling you down, and there's the normal reaction pushing you up. So those are the four forces. So Newton's second law, mass acceleration is equal to the resultant force. So mass acceleration, this is just n1 equals to mg. Mass acceleration, so mass acceleration is equal to resultant force, which is F, minus mu n. Mu n1, sorry, mu n1, of course. And that's it. That's your Newton's second law. We write it down, and then we go to the second block. Now, things are more complicated for the second block. So what are the forces on the second block? Start listing them. N1. Okay. Vin, very good. N1. Where is N1? Where is it applied? Friction of surface and friction block. Okay, so Vin, N1. What is the direction of N1? Very good. There's N1 pushing down. There's N1 from the top block. By Newton's third law, they are the same. This N1 and this N1 is the same. So if the top block is pushing the bottom block up, sorry, if the bottom block is pushing the top block up, the top block is pushing the bottom block down. There's N1, then there's friction, and friction has to be opposite, mu N1. So friction is the opposite to that one. Newton's third law, mu N1. Then we have new forces. So we have mg, thank you, mg. And we have, there's no friction. It's a smooth table, so there's no friction, but there is normal reaction. Let's draw it somewhere here, normal reaction. I'm offsetting it from the center just so it's not the same as mg. So it doesn't really matter where you apply it. So N2. Now the block is not moving vertically, not moving vertically. And this tells us that N2 is equal to mg plus N1. Volodymyr, what do you mean that there's no friction between the two blocks? It says the friction between the two blocks is 0.4. So look, take a book, right? And I'll take my phone and I take this, another thing on top, right? So if I push the top bit, Can't do that. So I can make my phone move, right? Can make my phone move. So the phone, if I push it this way, the phone experiences a friction force this way. However, this bob experiences a friction force in the opposite direction. Okay. Once again, so if I push this in this direction, my phone experiences friction force in that direction, and that's what it causes it to move. This is what happens here. So the top block experiences friction to the left, but the bottom block experiences friction to the right, which causes it to move in the first place. So not moving vertically, so N2 is equal to N2 is equal to mg plus N1. And then we have Newton's second law. Newton's second law. Mass acceleration is equal to the resultant force. So mass capital M, acceleration is equal to, so it's accelerating to the right. It's accelerating to the right. And, aha. Interesting. Interesting. This is acceleration A1. Because we don't know whether they accelerate together or not. They're both accelerating, but not necessarily at the same rate. So this will be A2, MA2. So the bottom block is accelerating at A2. MA2 is equal to mu N1. Oh, that's it. Mu N1. Okay. So you can see that the bottom block has the same well, is limited because mu N1 is a known value. Okay. So mu is, why am I doing this? Is equal to mu N, which is 0.4, and N1 is 1 kilogram. 0.4 times mg, mg, so 0.4 times 1 times 10. So that's 4 newtons. So acceleration of the second block is equal to mu N1 divided by capital M. So that's 4 divided by 3. So it's 1.33 meters per second squared. Okay. Sorry. Yeah, I'm jumping a little bit ahead, a little bit ahead of myself. I shouldn't have done this. I should have said that mass acceleration two is equal to the friction force, and the friction force is less than or equal to that. Because mu N1 is, we don't know whether it's sliding or not. We don't know whether it's sliding or not. Therefore, we can't say that it's equal to mu N1. It's the force of friction. Force of friction. And here, force of friction. Sorry for the confusion. And force of friction is less than or equal to mu n1. So force of friction is less than 4. Therefore, acceleration is less than or equal to 1.33. So acceleration of the stop block is less than or equal to 1.33 meters per second squared. In other words, we have a maximum value for the acceleration. So how does it work? Well, if you push too hard, the stop block starts sliding. If you keep increasing the force, the friction force will not increase. It will increase at first. I remind you that if you have a stationary block on a table and you have a force F and the friction force increases to a maximum value and then levels out. This is how the friction force, which is here, friction, and this is the pushing force. It has a maximum value when mu n. So friction increases and then levels off. This is what happens here. Now, A2. So now let's have a look here. MA1, so it's 1 kilogram multiplied by A1 is equal to the pushing force, which is 2 newtons, minus the friction force. And from here, we know that mass acceleration is equal to the friction force. So it's equal to 2 minus mass acceleration 2. Okay. I don't want to make it even more complicated. Let's write down some words. So friction can only be up to 4 newtons. So when we push with a force of 2 newtons, we will not exceed the limiting friction. Okay? Because as you can see, the friction is equal to the pushing force until a certain moment. In our case, this is 4 newtons. In our case, this is 4 newtons. But we're only pushing with a force of 2 newtons. So the friction force is 2 newtons. 2 newtons. Okay? So if the pushing force is less than mu n, then the friction force is equal to the pushing force. No, the top block accelerates. This means the top block will not slide. The two blocks will accelerate together. So A1 is equal to A2 equal to A1 is equal to A2. And we can use that. So we have mass A1 is equal to the pushing force minus friction, pushing force minus the friction, and MA2 is equal to force of friction. And we know that the acceleration is the same. We just add them. And we have m plus m multiplied by acceleration. It doesn't matter A1 or A2, and is equal to F. In other words, acceleration of the second block, well, acceleration of the second block, let's put it this way. Acceleration of the second block is F divided by m plus m, which is 2 newtons divided by 1 plus, is it 3? 3, yes. 1 plus 3. This is 0.5 meters per second squared. Now, in problem B, the pushing force is many times greater than the maximum friction force. Therefore, the top block will slide, and the force of friction is equal to mu n, which is equal to 4 newtons. And now we can solve it. So we have MA1 is equal to F minus force of friction. MA2 is equal to force of friction. So from here, we're not really interested in what happens here. We know that A2 is equal to force of friction divided by m, which is 4 newtons, divided by m, which is 3 kilograms, which is equal to 1.33 meters per second squared. Okay. I hope this makes some kind of sense. Sorry for being vague about stuff, but yeah. I forgot that there's a catch in this problem. So it's not as straightforward. But the logic is the same. You have this and this. You just need to look. So this is a question about the properties of the friction force. So it's a bit more interesting than expected. Now, in your assignment, you have a very difficult problem with a trolley. Okay, wink, wink. This problem is very similar to that one. What is the minimum force that needs to be applied to M so that the block of mass M is stationary? So what do we see? Well, we see a prism, a triangular prism, and we're pushing it. And if we push it hard enough, the top block won't slide down and won't slide up. So the top block has to be stationary relative to the bottom block. Okay. So what can we do here? Well, we can do the same stuff that we did before. We write down newtons Second law, we'll draw the free body diagrams first. So the first, the top block, we have mg, we have normal reaction, and that's it. This is, and they accelerate. They accelerate together, and the acceleration is a. So this is mg, this is n. So was the acceleration for the top block acceleration relative to the bottom block for problem 2? No, relative to the ground. A1 is relative to the ground and A2 is relative to the ground. We're not taking the relative acceleration. The relative acceleration would be A2 minus A1. They're not asking us for A1, so we kind of forget this. We don't need this. We just use this. So I hope that makes sense, JP. So here, the prism, the top block and the bottom block, they accelerate together. Stationary simply means accelerate. Accelerate together. All right. And this mass is accelerating at A. So it's not moving vertically. So here we do quite an unusual thing, because normally we split into components up and down the slope. But because we're not moving along the slope, it doesn't make sense to do it that way. It makes sense to do it parallel and perpendicular, well, vertical, up and down. So this is going to be n. This is 30. So n sine 30. And this is n cos 30. So because it's not moving up or down, and that means that n cos 30 is equal to mg. Now horizontally, ma is equal to n sine 30. Simple as that. Because that's the only force pushing it horizontally. And well, here you can figure out that n is equal to mg divided by cos 30. So you have ma mg divided by cos 30 sine 30. Okay. M cancels. So acceleration is equal to g tan 30. And tan 30 is square root of 3 over 3. So it's g divided by square root of 3. That is beautiful. I like it when it does this, square root of 3. Now let's look at the bottom block. So we have mg, we have n from n2, we have n pushing from the top. We have the top block pushing. We have the floor pushing up. We have the gravity pulling down, and we have a horizontal force F. So which force do we need to split, guys? Which force do we split into components? N, of course. Well done. Yes, N. We don't split any other force, and you can see that it becomes super easy when we do this. So this is N cos 30. This is N sine 30. So it's not moving up or down, again, not moving up or down. And that means mass mg is equal to mg plus n cos 30 is equal to n2. But this information is pretty useless to us, like honestly. We won't be using it. And then horizontally, we have mass acceleration is equal to the force pushing along this, so that's F, minus the force pushing left, and the force pushing left is n sine 30. N sine 30. Okay, so F is equal to ma plus n sine 30 equals m times g over square root of 30 plus n sine 30. That's, well, that's that. It's ma. That's actually ma. So mg square root 30, square root 3. So it's m plus mg divided by square root of 3, and that's the answer. Okay, how well did you understand the last problem on a scale of 1 to 10, please? Nice, some 9s. Okay. In the assignment, you have sorry. You have the problem about the trolley. And that's pretty much the same ideas. So the trolley is attempting, so this mass is pulling this mass down. But if you push it hard enough, this won't allow the acceleration of the bottom trolley basically will match the acceleration of the top, and it won't slide at all. So in this case, you draw the top. It accelerates. It accelerates due to the tension. That's the top block, 8m, and it accelerates because of the tension. So 8m a equals tension. Right? That's the Newton's second law for this one. So for this one, Newton's second law, well, it's only vertical, so we have tension, and we have 5 mg. So tension is 5 mg. Because it's not moving up or down, so tension has to be equal to that. And then for this one, F, well, that's a tricky thing, because you'll need to see what's actually what's going on in here. So what are the forces? So there's actually tension here, then there's this block pushing that way. Yeah, this block pushing that way. There's this block pushing that way. That doesn't really matter, because you only need the horizontal forces. So yeah, so there is something to it. How much time do we have? Oh, and this is very similar as well. I don't think we'll have time to do this one. but we certainly can do this. Okay, so find the tension in the rope if M1 is 100 grams and M2 is 300 grams. So this is a system of pulleys. Okay, so M1 is 100 grams and M2 is 300 grams. So which way do you think M1 will accelerate? M1 will accelerate up. Now, if you don't guess it correctly, it's not a big deal, because if you don't guess it correctly, you'll just get a negative A. Okay. So if you sometimes you don't know and you just guess. Okay. M1. M2 will accelerate down. What would be the acceleration of M2? And if you are able to answer this question, you are able to solve this problem. If M1 is accelerating at A, what is the acceleration of M2? Minus A. So do you think, so you think if this mass, if M2 moves down by 1 meter, M1 will move up by 1 meter. Do they travel the same distance? Ah, Sam, brilliant. Absolutely. Fantastic. You got it. Because if you imagine that the bottom, if the M2 moves down by 1 meter, M2 will move up by 2 meters. So acceleration of M1 is double the acceleration of this one. It's called a kinematic constraint. So M2 has acceleration downwards. I don't need to put negative. I put A over 2 down. The arrow shows that it is negative. Okay, so I don't need to say negative. So well done. If you, just think about it, if M2 moves down by 1 meter, by half a meter, M1 will move up by a whole meter. Well, this is to do with this, because with the way M2 is attached. The way M2 is attached. So this point is stationary. So let's say we pull on M1. We pull on M1, and M1 moves a distance x. That means this point moves up by x. Moves up by x. Yeah? So if M1 moves down by x, this point on the rope moves up by x. But if this point moves up by x, this point moves up by only x over 2, half. If you draw the triangle, this is x, and this is the midpoint, the middle line, so this is x over 2. Does that make sense? It's for a moving pulley. This is a fixed pulley. This is a fixed pulley. This is a moving pulley. Moving pulley. A moving pulley is a force multiplier. And if it's a force multiplier, that means it is if a pulley is a force multiplier, then the speed decreases by 2, by a factor of 2. Well, what is the center of the pulley attached to? If the center of pulley is attached to the mass, that means it is moving. If the center of the pulley is attached to the ceiling, it's not moving. Pretty much. Is M2 attached to the pulley or the rope? Well, pulley, of course. I mean, how can it be attached to the rope? I mean, okay, the picture is not very clear, but we don't attach masses to ropes, right? So why is the right of the not fixed pulley stationary? Why the other end? Why would the right stationary? Because this rope is fixed to the ceiling. So this point is fixed. That means this is also fixed. So this is the part of the pulley that is stationary. And the pulley kind of rotates around this point. Well, it's a lever. Look, it's a lever. You have this end is fixed and this one is allowed to move. Yeah, so if this end moves by 10 centimeters, the middle moves by 5 centimeters. Well, it's not fixed on the left. Yeah, it's only fixed on the right. So if you tie the mass to this point, yeah, certainly it will not move. But you're not tying the mass at this point. You're tying the mass to the pulley, and the rope slides under the pulley. So this pulley moves, and now this end is not attached, so it is allowed to move. So yeah, they do move. They only attach at one end. I mean, find a video on pulleys. It's incredibly interesting actually to have a look at how a pulley works. But yeah, this is the hardest bit about this problem, is just to figuring out that the accelerations. This is, as I said, it's called a kinematic constraint. So this pulley is accelerating down at a/2, and this pulley is accelerating up. And now all we need is Newton's second law. So for M1, we have M1G, and we have tension, and it's accelerating up. And that means mass M1A is equal to T minus M1G. For the second mass, we have M2G, and now we have two tensions here. We have tension 1, we have another tension, so it's 2T, double tension, and the acceleration is a/2. We have two ropes pulling with equal force, and you write down that M2 acceleration over 2 is equal to M2G minus 2T. And since you have all of these values, you just solve simultaneous equations. Okay, so so these are simultaneous equations. Solve for t. Is it? Are we looking for t? Are we looking for the acceleration? Yeah, we're looking for t. Wait, when the pulley of M2 moves, doesn't the length marked in blue change in length? Yes, but at any given moment in time, so Elliot is asking a very good question. If this pulley is moving, this rope changes its length. That is true. But this point, at any given moment in time, this point is not moving. By this point, I mean the right end of the pulley, not the particular piece of rope. The right end, this point on the pulley, this point on pulley is stationary at any given time. Okay, does that make sense? It's like a wheel rolling on a road. The bottom part is stationary. I mean, you can't say the wheel is stationary, and you can't say the road is stationary relative to the wheel, but you can say that the bottom, at any given moment in time, the bottom part of the wheel is stationary. Okay, finally, we have this one. We have a prism with a pulley and a rope, and there's friction. Okay, there's friction between the prism and the block, between the mass and the prism. There's friction between the prism and the floor. What is the force needed to make the prism accelerate at A? Okay, so it looks super complicated. Well, and it's once again, it's very similar to the problem that you have in the assignment. It's one of the harder problems. So you have tension down, tension left, because it's the same rope, same tension, mg. So, okay, draw mg. So we have mg. We have the normal force from here, and let's call it N1. There's a friction. So we're pushing this. So there's a friction force going down. So there's a friction force. There's a mu 1 N1. There's tension going up, and it's accelerating. It's accelerating at A. Okay, for the prism. So at this point, at the block, there's tension going down, there's tension going left, there's a force pushing, the force of pushing, then there's the friction force. There's N1, sorry, N1 from the mass. There is friction force going up, and mu 1 N1. There is friction force here, N2 mu 2 N2. There's the normal reaction here, N2. And that's it. I mean, does sound complicated, but all you need is just to draw, is write down the equations and solve the simultaneous equations. So this one is accelerating to the right. This one is accelerating to the right. So we have m capital acceleration is equal to f minus t minus n1 minus mu 2 n2. And for this one, ma is equal to t minus mg minus mu 1 n1. Okay, and horizontally, we have n mass acceleration is equal to n1. And here we have vertical forces, because vertically it is not moving. Vertically not moving. We have N2 is equal plus mu1 N1 is equal to T plus mg. Yeah, forgot mg. And you have one equation, two equations, three equations, four equations, and the unknowns is F, N1, N2, and tension. Ta-da! We have four equations, four unknowns. You can do it. Like, I mean, I don't have to solve it to say that there is a solution, because I already see A is given. What is the force needed to make the prism accelerate at A? So A is given. And mu1, mu2 is given. So four equations, four unknowns, you can do it. Yes, they are. They are. To answer this question, you just need to imagine that the bottom prism moves by a distance x to the right, and you will see that the mass will move x to the right. That means it has the same acceleration to the right. And it will also move x upwards. That means it has the same acceleration upwards. So I did say that it's going to be the same acceleration, but it doesn't need proof. I've just made my life a little bit easier. Well, yeah, I mean, this is not just about physics, it's about any problem. Any yeah, I mean, if worded proof is acceptable, definitely. That the acceleration is the same. As long as you make it clear why you think the acceleration is going to be the same. If you move by a certain distance, this will move up the same distance and move right the same distance. So it has the same acceleration up, the same acceleration to the right. Yes, any problem can. So if a problem does not break down into simultaneous equations, this problem is unsolvable. That's fundamental. Because we haven't learned how to solve anything else. We only know how to solve simultaneous equations. All right, so enjoy doing physics, and yeah, see you. Oh, you might not see me next week. I will be in touch. I'm going away, so hopefully somebody else can do the webinar. I'll let you know anyways. See you.